Alright class, so let's finish up kinetics and then we're going to do a lot of practice problems today to make sure you get this chapter down. So the last thing I want to talk about is catalysis, okay? Let's say I have this reaction and this reaction has a delta G that is negative 234 if we haven't got to delta G yet. So delta G negative means a reaction will happen. So this means the reaction will happen. And then here the delta H is negative 196. So it's an exothermic reaction. So what that means is thermodynamics tells me that this reaction will happen. It's thermodynamically favorable. Okay, well that's great that thermodynamics tells me that this reaction is going to happen, but we all know we also need to care about kinetics. Well, we know it's going to happen, but is it going to happen today? Is it going to happen 100 years from now? What is the timeline? What is the speed of this reaction? So here's the deal. If we have no catalyst, if we add no catalyst to this reaction, the activation energy is going to be 75 kilojoules per mole. And then if we have I minus as a catalyst to this reaction, activation energy is 59. If we add platinum powder as a catalyst, the activation energy is 50. And if we add enzyme to this catalyst, liver catalase is a specific enzyme that we could add, the activation energy would be 25 kilojoules per mole. Okay, so no catalyst, and in all these three cases, there is some sort of catalyst. Now, why is it the activation energy goes down when I have platinum powder as a catalyst versus I have I minus as a catalyst? What do you think? So when you have powder, what does that mean? Powder, that means you are more exposed, right? You are more exposed. You have a larger surface area. So, okay, that's going to bring down the activation energy even more. And enzyme, if you have an enzyme, the activation energy is 25. Remember, we can never do anything as good as the nature. The enzyme in our bodies, those are just amazing catalysts, and we will never be able to even compare those to the catalysts that we add in lab. So nature does it best, and we can't compete with nature. Remember that. Okay, now what does this mean? So when you add a catalyst, the activation energy goes down. Okay, so catalyst lowers the activation energy. I want to write that down. So catalyst lowers the activation energy. Okay. Now, this is going to be very interesting. I want to put time next to this. So if I add no catalyst and the activation energy is 75 kilojoules per mole, what that means is this reaction is going to happen in 2 years. You have to sit there for 2 years to make this reaction go. Good luck with that. Hopefully you have better things to do. If I add I minus, then it's going to happen in 12 days. Oh my God, look at that. Huge difference. If I added platinum powder, now it's going to happen in 40 minutes. And if I added enzyme, it's going to happen in 1 second. So you really need a catalyst to make this reaction feasible, right? And again, like I said, oh my God, nature does it best. We can't even come close to that. So far, so good? Okay, so catalyst lowers the activation energy. Now, how does it lower the activation energy? What it does that, I want to write this down to make sure you understand this and you have it in your notes. What catalyst does, catalyst alters the reaction mechanism. Catalyst alters the reaction mechanism. So far, so good? Okay. Now, I want to show you what this means. What does it mean that catalyst alters the reaction mechanism? Well, let's talk about it. I'm going to put up a chart. This is going to be energy, okay? Now, what we had 2 hydrogen peroxide going to 2 H2O and O2. That was our reaction. And if I don't have a catalyst, here is the pathway. Oh boy. Let's see if I can do this. Okay, not too bad. This is a pathway if I don't have a catalyst, okay? And remember, there is a hump that you have to get over. There is a hump that you have to overcome, right? We talked about it. There is a hump that you have to overcome. So far, so good. Okay. Now, if I have a catalyst alters the reaction mechanism. Now, this is going to be my new hump. Now, this is going to be my new hump. Okay? So it's altering the pathway. Is altering the pathway. So far, so good. Okay. Now, for the reaction that was not catalyzed, this was the activation energy. This was the activation energy. Okay. Now, for the reaction that is catalyzed, the activation energy is right here. That is the activation energy. Okay. So it lowered the activation energy by altering the reaction mechanism, by altering the path. Okay. By altering the path. Now, there's one thing I want you to pay attention to. Catalyst only alters the hump. So it's going to alter the path, it's going to alter the hump, and it changes the activation energy, but it does not do anything to the product and reactant. Okay? I'm going to repeat this again. So catalyst only alters the hump, and it changes the activation energy, but it doesn't change anything about product and reactant. So what that means is it doesn't change the delta H. Right? Because if you remember, delta H of the reaction was product minus reactant. It doesn't do anything. It does not change that. It does not change delta H because it does not change the product and the reactant. The only thing that it does, it alters the pathway and it changes the activation energy. But it does not change anything about the product and it does not change anything about the reactant. So the delta H will remain the same. Sounds good? Okay. Beautiful. Now, there's 2 more graphs that I want to put up. And then after that, we are done. Promise you. And you've heard that too many times at this point. Probably don't trust me. Alright, so let me put up a graph. And I want you to put this graph up with me. Okay. Let me see. I want to go from here to here. Okay. And then I want to put another graph up on the right side. So put this graph over for me and I will explain these graphs in a second. So remember that we have reactant here. And you always have product, right? Reactant going to product. So far, so good. Okay. Now, this is a pathway without a catalyst. Okay. And of course, if I had a catalyst, the pathway would change. But that's not the point here. So here's, I have 2 reactions. Reactant going product, reactant going to product. What's the difference between these 2 reactions? The reaction on the left, the product are going to have a lower energy than the reactant. When that happens, what that means is you have an exothermic reaction. So exothermic reaction, the product have a lower energy than a reactant. That's why it's favored, it's exothermic. You're going to form something that is low in energy. That's good. So it's favored because, again, you're going to form something that is low in energy. That's great. Now let's look over here. I have reactant. Product has a higher energy than the reactant. What does that mean? That's an endothermic reaction because you are forming something that is higher energy than what you start with. That's endothermic reaction. So far, so good. Okay. Now, the activation energy for this one will be from here to here. That would be the activation energy. Okay? And if I add a catalyst to it, the catalyst will alter the reaction mechanism, it will alter the path, it would change the hump, and it would change the activation energy. So if I add a catalyst to it, it would be something like this, right? It would alter, remember, catalyst would alter the activation energy by altering the path, the reaction mechanism. So far, so good? Okay, beautiful. We are done, promise you. Now let's do practice problem.